Hey everybody, welcome back. Professor Gusimi here. And if you've come to learn about AI agents, you're in the right place. Today's lecture is about prompt engineering. Specifically, we're going to be talking about three subjects. First, we're going to go over the motivation for prompt engineering. Why does it exist? Why are there prompt engineers? The second thing we're going to do is come up with some definitions. What is a prompt? What is a prompt template? And finally, of course, what is prompt engineering? And then what we're going to do is give a survey of prompt engineering techniques. Think of this as a rapid-fire review of a large collection of academic papers and studies they've done on what works in prompting and what doesn't. We're going to do this by taking dives into what a set of scientific papers say about various prompt engineering techniques, coming up to the surface, synthesizing those so that you get key takeaways that will help you do better in your own prompt engineering journey. So let's get started. First, the motivation. Well, just recall, this is an AI agents class. And I think we all know that prompting is an essential part of an AI agent. Why? Because the actual definition of an AI agent is a Gen AI system that can serve a user's goal by actions that engage with systems outside the Gen AI system itself. And at least as of 2025, these Gen AI systems are most often, for a large number of use cases, LLMs. So what I have here on the right-hand side is a depiction of what an AI agent is. You can see here in the middle, we've got an LLM. And then as we discussed in the introductory lecture to this class, the LLM has access to some tools. This could be databases, APIs, Python functions that have been written, or C functions for that matter. There's some memories, which might be stored in an in-memory database or a regular standard database. And there's some planning capability. And this LLM, when augmented with these additional tools, allows it to interact with the environment, which could be user queries, to do more than what an LLM alone could do. This is what makes an AI system an agent. But if we're going to have an LLM at the middle here, well, the prompt is going to be important. And it's going to be important because most good agents use good prompts. Of course, not all good prompts make for good agents, but definitely most good agents use good prompts. I've got an example here. On the left-hand side, you can see a user asked this system, in this case it's Gemini, is there anything wrong with this photo? And I'll give you a minute to take a review of it. I'm sure after you've done that, you can pause the video if you need time. If you'll come to count the fingers, you'll notice there's 1, 2, 3, 4, 5, 6. Most human hands don't have 6 fingers, albeit this particular depiction of a 6-fingered human hand is pretty realistic looking. So if you come here to Gemini Experimental and 1206, and you give no system instructions, so it's basically prompt free, and other than what you asked it here, you can see that the model gets fooled. It thinks there's nothing wrong with this hand that has 6 fingers. If you update the prompt, specifically the system instructions, to tell it that it's a very careful, meticulous, and detail-oriented assistant, well, you can see now it seems to understand that there is, in fact, something wrong with the photo. And in fact, it identifies that normal human hands have 5 fingers, and there appears to be an extra finger between the index and the middle finger. Okay, very interesting. So the prompt matters. But what's the problem with prompting? Why is prompt engineering sort of a controversial or a challenging term for some people? Well, it's because there's practically an infinite number of ways to engineer a prompt. I've given you an example here on the left-hand side. Let's say you're a marketer, you're attempting to come up with the best possible prompt to explain a product to your customer, and you have a prompt template like this. You are a role at a company. Your task is to task for product, and each of these are variables in sort of a Python programming sense. In the industry, the audience is audience, located in region. Use a tone that is tone, and format your response as format, emphasize, and then you can put a priority. So let's assume you want to iterate across a set of prompts, and you want to find the best prompt. And the way you're going to do that is for each of the 10 variables that you have here, you're going to try 10 possible configurations. So 10 roles, 10 companies, 10 tasks, 10 products, and every combination thereof. You would need, if you wanted to explore this space entirely, 10 billion prompts. And based on the last price check I did for even a reasonable model at a reasonable price, you're going to end up spending something on the order of $500,000 to get the answers to those prompts. So not going to be cheap. Okay, so this is the reason sometimes people draw an analogy between prompt engineering and using a slot machine. This is an image that I took from the World Wide Web that I found on a LinkedIn post a few weeks ago. And they sort of make an analogy between prompt engineering and maybe vibe coding, which is a common way to approach prompt engineering. The tokens that are purchased are sort of similar between the two. Just as you're pulling a lever in a prompt machine, you're writing vague prompts and hitting generate and so on and so forth. So there's got to be a more principled way to do this, right? And the purpose of our lecture here today is to see if we can explore what the scientific literature says about the most principled ways to perform your prompt engineering. Okay? If before we dive any deeper, you remember nothing else, what I've got down here are a set of prompt engineering techniques. We're going to cover most, but not all of these in the lecture today. And what I have here is the number of citations associated with each of these categories of prompt engineering techniques along the x-axis. And so if you remember nothing else, know that few-shot learning techniques, which is where, as we will discuss in a few slides from now, you take some examples and you put them inside the prompt to teach the language model how to generate higher quality responses, is the most common approach. Doesn't mean it's the best approach, but it's the most common. Okay, so with that, we've covered the motivation. What's the synthesis there? Prompt engineering is important. The quality of your prompt impacts the quality of your response. I think we all know this anecdotally, and there's evidence beyond anecdote that shows that, a lot of which we're going to get into today. Before we dive into what the specific methods are, let's just get perfectly aligned on what a prompt is, what a prompt template is, and what prompt engineering is in the formal sense. Okay? More specifically, we're going to be covering in this taxonomy of key terminology. This taxonomy, by the way, is contained in the paper in the bottom right-hand side here. This paper is also what we're using to draw all of the various prompt engineering techniques from. Really nice piece of work. It's from February of 2025, so just this year. They did a systematic review of key terminology within the prompt engineering, let's say, community, the people who use prompt engineering and test prompt engineering methods. But more interesting and importantly, they did a survey of all the techniques and tried to figure out which of those were sort of more or less effective on the basis of the results presented in the studies. That's what we're going to be covering in a bit. For the purpose of this lecture, I'm only going to focus on some of the key terms around prompting. And the reason is a lot of the other terminology in the taxonomy that I've shared are things that we will be covering as we go through the methods themselves. So I don't need to cover them twice. I'll just give you the basics and then we'll dive into the specific methods. Okay, let's start with what a prompt is. That is an input to a Gen AI model that guides the output. Okay, that's what you plug into ChatGPT, Gemini, or an image generation tool for that matter. And we all know that small changes in phrasing, order, and context can produce different results. If you think about the anatomy of a prompt, the various pieces, there's not one global standard for what the various components of a prompt are. Although later this semester, we are going to be talking about certain protocols people are putting together for what the inputs and the outputs to AI agents should look like following evolving protocols that are being generated by industry and academic collaborations, agent-to-agent protocols specifically. But for now, let's sort of think of the most simple anatomy of a prompt. Well, you have a role, that's kind of the persona. You have instructions, that's what you want to do. You have some context, that's background and examples you provide. There's some input data, that's what you want to process, and then there's some constraints. What do you want the format, the style, and the length to be? Okay. I have here on the right-hand side an example prompt. You're a helpful high school tutor, and you can see I've color-coded this. Helpful high school tutor is an example of the role. Summarize the following text as an example of the instruction. Hegel's phenomenology of spirit is the input data. And of course, drawing from what the work says directly and limiting to 4 sentences with some additional stipulation is the constraints. This example prompt would probably be useful because if you know anything about works of Western philosophy, Hegel's writing is not, let's say, accessible to many people who are not really steeped in the traditions of reading academic philosophy. Okay, and so if you were to give this example prompt to ChatGPT, which I did a few hours before this lecture, you get a very reasonable response which covers Hegel's phenomenology of spirit. Of course, if you change aspects of this prompt, such as the role, from a helpful tutor to a pirate, you get a rendition of this with all the things you'd expect of a pirate. The R's, the refers to chests of gold, references to chests of gold, and lots of use of dropping of a G and replaced with a hyphen and so on and so forth. Okay. If we change the constraints down here to be responding with a haiku, we can now get a pirate that is summarizing Hegel's phenomenology of spirit, responding with a haiku, which I actually thought was quite nice. Conscientiousness sets sail, clash and stages mark the way, spirit finds its home. If you're a fan of haikus and you know anything about Hegel, I actually think this is shockingly good. And I think that the pirate affect actually adds something to it. So anyway, silliness aside, a typical prompt template, if we were writing it in Python code, looks something like this. It's just a string, and it's a string that has certain variables that we might want to plug in, x1, 2, 3, 4, and 5, which again here have been color-coded to correspond to, let's say, the role, instruction context, input data, and constraints that we have. And then what we would do at the time of running our analysis is to fill this this template by substituting x1 through x5 with something that we're interested in. Okay, so that's what a prompt template is. String, we pop in contents, we get an output. Prompt engineering is a series of steps we do to infer, evaluate, and modify the text that goes into a large language model or other generative AI system so that we get the best quality output. Typically consists of a series of steps here, which I'm going to step you through. Okay, the first of these is coming up with some data points that you want to process or analyze. Raw input for prompting the model. This could be, as an example, a data set of 1,000 customer reviews, and maybe a subset of these we've annotated. So let's say 10 of them, we have a ground truth from a human that tells us whether the review was good or bad, but we'd like an LLM to help us with annotating the rest of them so that we know what people had to say about all of the reviews, and we don't have to sit and manually annotate 1,000 of them. Okay, well, the first thing we do after we had that data organized is we'd come up with a prompt template. We just saw on one of the previous slides what that is. Structured input format with placeholders for variables that guide the model on how to respond. In the case of this review, maybe it would be summarize the review for a product in a certain tone. Okay, we then move to this generative AI phase where a large language model would take the prompt template and it would plug in for each of the samples, the review, and maybe a tone that we were interested in. And it would generate a succinct summary of the customer review. So we would then take the output of this generative AI system, and depending on how we constrained it in the prompt, we may have to do some extraction. So for example, we might have a component here that parses what came out of the generative AI model, that formal statement, and extracts a sentiment from it. So we see if the word positive, negative, or neutral came from the generated summary. Importantly, we don't have to do that. We could also just write the prompt template in a way where it tells us whether the output is positive, negative, or neutral. For some tasks, though, these extractors are used, which is why I included it. Finally, after we've done the prompt template, we've passed it to the generative AI system, we've done any extraction of the output, we come here to what's called a utility function. And this is a scoring rule that measures how well the output meets the desired goal. We might compare that extracted sentiment with the ground truth labels I mentioned at the beginning. Remember how I said, let's say out of these 1,000 reviews, we had hand annotated, I don't know, 10, 20, something like that. We can go check, hey, for the prompt that I used and what I extracted, on that 10 that I actually know what the ground truth is, how well did we do? If it got it right on all 10 of them, it's probably going to do well on the remaining 990, and we can move forward. But if it catastrophically failed by getting only 3 out of those 10 right, we probably have to go back and iterate through this, right? Start again from the top, change how we've written the template, maybe try to address some of the deficiencies that we saw in that test set. So this process, starting from a data set, some of which is annotated, coming up with a template, passing it to a generative AI system, doing some post-processing, and then assessing the quality of the output. When you do that over and over and over again, you're prompt engineering, okay? The question that you would naturally ask is, how exactly should you adjust the template? So when you've started and you've done one complete cycle of this and you've run your utility function and you know, let's say that your prompt template is terrible, what do you do to make the prompt template better? That's the really important question to get us away from the slot machine analogy I brought up earlier. And that's what prompt engineering techniques, many of which we're going to be covering in significantly more detail as we go to the next component of this lecture, are going to teach us about. Briefly, prompt engineering techniques are how you improve the prompts on each of those iterations of the prompt engineering cycle. Okay? I'm giving you one example here. Let's say we have a problem description and we have some prompt instructions. There's a tool which is referenced down here, Prompt Wizard, which is by Microsoft. They take the prompt and they come up with several mutated, they call it, versions of this prompt. So they swap out synonymous terms, they expand or contract certain parts of the prompt randomly. And then they take some of those training examples. Those are the annotated set, like in the context of the movie review I mentioned previously on the last slide. And they score it. They say, hey, which of these mutated version of the instructions tended to do the best? Okay. They come and they look across that set. They say, it looks like one of these really did well. This one did the best. So let's have another LLM critique this, say, was there anything wrong with this top prompt? Basically, did we get this at a chance? Or does it seem like this particular instruction set that we arrived at here is really, it's solid, it's bulletproof, it's going to generalize, and so on. It critiques that. Maybe we make some modifications to it, and we start again now with a revised prompt, which we continue to do that mutation on in a cyclical form like this until we converge to some score here that we find acceptable. So you can see this is very much an engineering problem, right? We have these green blocks, which are calls to a large language model, maybe with the exception of score, although it could be done with a large language model. And then we have a sequence of steps that we perform in order to sequentially improve the prompt up to some convergence criteria with a score we've defined, okay? That's an example of a principled prompt engineering technique. There's another category of techniques that people use to come up with better quality prompts, and specifically prompts that do well on specific tasks, usually when you have sets of these tasks actually, called prompt tuning. What this does is it learns a small set of new model parameters called soft prompts that are tailor-made for the particular task or set of tasks that you're working on. For clarity, in today's lecture, we will not be talking about prompt tuning. We might cover that in later lectures deeper into the semester. For now, I just want to make you aware of what prompt tuning is. You take a set of trainable vectors, those are what are called soft prompts, and you prepend them to the input. So if this was your input text of your prompt, okay, if we were talking about the reviews earlier, I want to review this product in this tone, you basically prepend some vectors here to the front, some tokens, and then you fine-tune the large language model so that it can't touch the representations of the tokens that are here in the input text, but it can learn how to adjust something here on the soft prompt. And when you're doing fine-tuning, obviously, you give it those annotated examples, let's say of which reviews had positive or negative sentiment that you had manually annotated. What this allows you to do is come up with a set of these tokens here that help the pre-trained language model GPT, Gemini, Llama, whatever you're using, do better on the tasks. They're sort of specialized for the tasks without touching the internal representations of any of the tokens in other parts of the system. Okay, this is great because if you're trying to train a language model and you don't have a lot of computational resources, or you don't want to subject yourself to some kind of nasty effects of fine-tuning large language models like catastrophic forgetting, prompt tuning can sort of get you all the way there. Now, of course, again, prompt tuning is not prompt engineering, which is what we're covering today. Prompt tuning is not full fine-tuning. I'm bringing it here more as an FYI for you, so that if you want to look into it on your own in advance of lectures later in the semester, you can. Okay, so I think we've covered most of the main terminology here, right? The things that you'll hear about scattered throughout the scientific literature or topics that you'll find on the internet that discuss prompting, you'll hear these sets of techniques covered. As I mentioned, there are a large set of other terminology here in this taxonomy, which you can read more about by visiting the archive paper referenced here in the bottom right. There's definitions for each of these provided. I don't think you'll need to, because we're going to be covering the ones that are most important as we go through the remainder of the lecture here together today. So let's jump into that. This is the survey of prompt engineering techniques. So just as a reminder, if you jumped to this part of the video, what we did is we took a survey paper, the same survey paper I referenced a little earlier in the lecture, and back in February of 2025, they looked at a ridiculously large collection of papers that had studied the effects of prompt engineering. And they tried to take all of those approaches and put them into buckets, into groups, so that we could think through what are the categories of these techniques, how well do these categories tend to work, what are the subcategories of those techniques. And what they reported is that there's basically 6 of them, 6 groups of these techniques. They are, as I'm listing here, zero-shot techniques, which refers to prompting with 0 examples, few-shot techniques, which is doing prompting and including some relevant examples to help improve performance, something called thought generation, which is synonymous for chain of thought, which we'll be talking about a little later. This is where you prompt the LLM to articulate its reasons when it's solving a problem. There's ensembling, which is prompting multiple agents and aggregating the results. Self-criticism, which is asking the LLM to criticize itself, similar to what we saw in the prompt wizard example. Remember, they had this little block that said, hey, we're going to ask the LLM after it's come up with the prompt that has the best score, let's have it criticize itself to make sure that score wasn't there due to an artifact of some kind. And then, of course, we have decomposition, which is taking a big prompt that has a lot of complexity, a lot of steps, breaking it into little prompts that are easier and can be distributed out either in parallel or in series to a set of language models or other generative AI models. What we're going to do at this top level is, from here on out, sequentially step into each of these 6 areas. And I'm going to give you a very fast pass through techniques in the literature that are within each of these 6 buckets. I will be going through it fast because the full papers are referenced. They will always show up in the same place here in the bottom right-hand side. I will be showing you a link to an archive paper or other reference you can use to see those papers. So I'll try to give you the gist of the techniques that are covered within each of them, along with a figure. Please do feel free to go and double-click on those if you want to learn more. A last thing for you to note is that after I've covered each of these 6 sections here, I'm going to zoom out and sort of give you a synthesis of what I think is most important to remember about each of the 6 groups. So let's get started with zero-shot. So zero-shot refers to a set of techniques that require 0 examples. And what I'm going to do is take you through very quickly some of the zero-shot techniques that have been covered and formally studied in the scientific literature over the last 2 years or so. And I'll try to call out for each of these what you should remember. Okay, the first one is a technique called emotion prompting. And so what this is at its simplest is you take a prompt, such as the one I have here, and you append to the end of this a phrase that would be of psychological relevance to a human, such as, this is very important to my career, right? So if you were asked a question by me and I told you, hey, your answer here is extremely important to my career, that would make you hopefully take pause if you were empathic and say, man, I better think super carefully about this. I don't want to mislead him with my answer. What the authors of the emotion prompting paper, which again is referenced right here, as all papers that I discuss will be, they found that you can get a 1 to 2% improvement in a few of the bigger large language model benchmarks simply by including a phrase like this at the end of your prompt. So useful to know. It may not hurt you to do this, but I don't think a 1 to 2% bump is a very large one. I think as we see when we go through these, there are sort of bigger wins to be had if you're going to be optimizing your prompting. Okay. Another one is role prompting. And so this is where actually what we did in the very beginning when we asked, as we discussed the definition of a prompt over Hegel's book, I changed the role from being a helpful tutor to a pirate right before we did the haiku. So role prompting refers to what that role is of the entity answering the prompt. Okay, you are a mother, lawyer, chatbot, and then you follow that with, where is the capital of the United States? That's an example of the role, this stuff here in the role prompting. And what the authors of this paper here did is they looked across a ridiculously large number of roles. It's really impressive. If you go to the bottom of their paper, you'll actually see it. And they tried to figure out if the role that you ask the LLM to play has a positive or negative impact on the prediction accuracy. And the short answer is it actually does have an impact, but identifying the best persona requires a really exhaustive search. So if you try to guess what the best persona is for a task, you oftentimes do no better than random selection. So what should you take away from this? Adding a role may not be critical. It probably won't hurt, but it's not likely it's going to help you. The only way you'd be able to find the right role is by doing a very exhaustive search for your task across a huge set of candidate roles. Okay, what about the style? What style you ask the LLM to respond in? Well, there was a separate study that looked into this, and their specific objective was to figure out if you ask an LLM to generate answers in one style versus the other, how well is it able to sort of obey those stylistic constraints? I'm showing you here an example from, these images that I'm showing you, by the way, are all lifted directly from the papers that are here in the bottom right. So as we move from one image to the other, it might look like we're kind of changing the way that we represent things because different authors of these scientific papers have different ways they like to represent concepts. But the idea here is pretty simple. So, you ask a large language model to write a passage about love with a humorous tone. And if you read this response, I don't know that this is particularly humorous. It adds words like hilarious. It notes that there's plenty of room for humor in love, but humor is subjective, so I didn't find this particularly funny. And I think the authors shared that in common with me. What they were trying to note here was the places where large language models can fail to follow instructions, both stylistically, here with the humorous tone, but also structurally, asking an LLM to write 10 words about running and getting a smaller number. The gist of what they communicated in their paper is that the nuanced styles are harder to pull off. Humor, satire, irony, passive aggression, these are hard to pull off. Simple stylistic controls like formal versus informal are easier to pull off. So if you remember anything, just know that the more complex stylistic elements are going to be harder for your LLM to help you with. Okay, there's another paper called System to Attention, where you ask an LLM to rewrite a prompt and remove information that's unrelated to the main question. So the idea here is extremely intuitive. You have a problem. This is the problem set that the author chose. It's sort of one of those math word problems that you have to do on your ACT or SAT if you took those exams. And what they're showing you here is that if you pass this directly to a model, you get the wrong answer. But what happens is if you simply ask as a first step a large language model to rewrite the prompt and remove the unrelated information, the stuff that's irrelevant for the question, in this case, Max having 1,000 more books than Mary, then what happens is you get the right answer. Okay, so what should you take away from this? Well, if you're dealing with a very large quantity of information and you're prompting, it might not be a bad idea to have a precursor step where you ask your language model to remove some of that irrelevant content. That's the gist of what they were covering here. Okay, let's go to the next one, the simulation of theory of mind. This is an interesting idea there, and it's a very simple one. So they said, if you have a sequence of, let's say, elements in a historical sequence of events, let's say, and you need to figure out from the perspective of one of the characters in that event series what the state of truth is, how do you get an LLM to take those perspectives? How do you get it to do theory of mind? And they basically propose you do it in 2 steps. So if you have a set of, let's say, data here with a full story written in text, the idea is if you want to know what the green character here, what their perspective on the story was, you simply take every part of the story that was related to the gray character here and you remove it. And then you ask the LLM to do its inference of what the truth is on the basis of only the data that this particular green character could see. So you could imagine if this was stored in a database and you knew which of the characters had done what at which time, you'd basically remove this row. Or if you had this all in text, you might, similar to what we saw in the S2A example previously, ask an LLM to remove all parts of the story that were related to the gray character's role. Okay, very simple idea, you just remove. Okay, the next one here is rephrase and respond. I think this one is also sort of thematically similar to what we saw in S2A a couple of slides earlier. But with an important catch. Instead of taking a prompt that's provided and asking it to remove content that might confuse the language model, you ask it to take a prompt that is vaguely written and write it more concretely so that mistakes don't get made. This is an example that they had in their paper. If you asked a question, was a person born on an even day? This is actually a vague or ill-posed question because day here could refer to day of the year. Day here could refer to day of the month, right? And so what they were trying to show here was you can take your prompt, ask basically an LLM prior to getting the final answer to rephrase the questions that are subject to multiple valid interpretations. I personally think it's better to just ask the user for clarity directly. So you shouldn't be posing questions like this probably to a large language model that are vague and open-ended, because if you ask an open-ended question, you might get the wrong answer. Okay, let's go through rereading. This one's extremely simple as well, as honestly most of the zero-shot techniques are, and I even think most of the stuff in prompt engineering is. Idea here is very simple. They say, take the input, give it to the LLM. Let the LLM respond. Give it the exact same input a second time. Let it respond again. Okay, the authors reported in tests that they did on benchmarks that asking it to reread the material and answer twice helps the model condition on the whole sentence when encoding each of the second pass tokens. And so this ends up helping for common sense and symbolic reasoning tasks. So it's kind of a poor man's way to just get a boost in your performance for certain kinds of tasks, is just asking the question twice and leaning into the second answer of the question. Pretty simple technique. Also seems to work. The last one we'll cover here on the zero-shot techniques is self-ask. This is where you have the model explicitly pose and answer sub-questions and then synthesize. So the example that they're showing here is you pose a question: who lived longer, Theodore Hecke or Harry Vaughan Watkins? And are there follow-up questions needed here? If the answer is yes, right, you ask the model yes, then you ask it to pose those questions and give you the answers. You then concatenate the whole thing, all of it together. So both the original question and the subcomponents feed it back, and this ends up improving the performance. Okay. So pretty simple, right? I mean, these zero-shot techniques, they're called zero-shot because you're not putting any examples. There's just a way that you're changing something about the instructions that are provided or other elements of how you interact with the language model, asking twice, asking it to synthesize things, and so on, that improve your performance. If that seemed like a lot, there's really three things that I suggest you recall about zero-shot prompting if or when you're using it. The first is to pick the tool for the failure mode. So if you have noisy kind of information that you need to do a task across, so there's like too much context, maybe you use S2A, which was the one that filtered out the irrelevant context for the task. If you have ambiguity, maybe you want to use R2R. If you have multi-hop sort of sets, the answer requires multiple steps in reasoning, maybe you use self-ask, and so on. So try to think about what the failure mode is of the task you're doing, and then write the prompt that fits, or use the zero-shot technique that fits the failure mode, specifically that resolves the failure mode. Okay, the second thing I suggest is that you force structure before answering. Okay, so have the model rephrase or decompose the question first and then answer. Okay, this will help trim errors. It comes at some cost, of course, but I think if you're in a mission-critical environment, some of the cost of asking for the rephrase or the decomposition is worth the increase in accuracy. Okay, I also suggest that these first three up here, the emotion, the role, and the style prompting, I think you can use these sparingly. I don't think they have a significant effect based on what the research shows, or when they do, it goes back to trying to play the slot machine, where figuring out what the right way to set the emotion, the role, and the style are ends up requiring a really brute force search across all possible roles, styles, and so on. Okay, so we've covered the first one. Let's move now to few-shot techniques, which is prompting with just a few examples. So there's a smaller number of these that we're going to be covering, 4 specifically, starting with exemplar generation. And so recall, before we jump into this, that the differentiation between few-shot and zero-shot is that a zero-shot prompting technique, you don't put any examples in. You just change basically how you write the prompt. What makes it a few-shot technique is that you're including examples. And so there's a natural question then, if you're going to include examples, of how do you generate the examples? What examples do you put in the prompt? And exemplar generation, which again is from the paper that's referenced down here, basically proposes a very simple fix. They say just let the AI generate the exemplars. So you self-generate, you put those into a language model, you do inference with the self-generated examples from up here, and then you get your output. Super simple. If you have your regular prompt, ask it to generate examples, append those to the end, you're done. Okay. This is better than zero-shot scenarios according to what the authors reported, but these generated samples that the LLM comes up with are never going to be as effective as actual data. So I would only use this if you're truly blind. You have no real examples that you can put of pairs of, given a question that looks like this, here's the right answer. Okay, the second thing you can do if you're going to be putting examples into your prompt is you can choose the order, right? So let's say we put 3 examples, A, B, and C. How do we order them? Do we do CBA, BAC, ABC? How do we order them? Well, it turns out that the order of the examples does in fact matter. And usually you don't put a large number of the shots or examples into your model when you're doing the few shot prompting. And so because of this, the authors of the paper on exemplar ordering said, look, if you've only got a small number of examples that you're providing, you can probably just iterate through all possible permutations of the order, and it won't cost that much for a small test set. And then just choose based on your test set, let's say the 10 reviews you had annotated from earlier in the lecture, take those, use it to choose what the right order for your prompts are. Very straightforward idea. Basically just try a bunch of orders, choose the one that's best. Okay, what about exemplar selection? So now, unlike the first one, exemplar generation, where we had no examples to pull from, what do you do when you have a set of data and you want to pull some of these unlabeled data sets? So these are movie reviews, you don't have the answers on them, and you want to pull these so that the LLM can help you with doing the annotation on those reviews. So the authors are asking, well, if you're going to include examples, how do you choose the best examples? And what they propose is that there's two steps. You take a large unlabeled data set, and then you come up with some selected unlabeled data. And how you do this selection, it might be through clustering, it might be through a thematic analysis. Hey, we have horror movies as a genre, we have comedic movies as a genre, let's choose, 2 from each or whatever. You annotate those, and then once you have the annotated set, now you're good to go, right? You just move forward with predicting what the performance is, testing, and going through that same loop over and over again until your prompt does well on that. So very straightforward. Basically, if you have a large unlabeled data set, choose a heterogeneous set of examples, annotate those, and move forward. Okay, how about instruction selection? Well, this one's sort of weird because the authors here were trying to investigate, if you have just a set of examples, let's say the movie reviews with the sentiment, and you wanted to get an answer where, you give it, for example, a new review and you wanted to give a new sentiment, does including this instruction up here help? And can you learn this from examples? So if you just gave some of the data, which was the movie reviews, should you let an LLM infer this instruction up here at the top? The answer they found was that almost all the time it's no, so you should not use an LLM to infer this. You should write it yourself. In all but a few cases, they reported that it's better to do that. Okay, so what do I want you to conclude from this few shot stuff? Just a reminder, few shot learning or few shot prompting, is where you take a few examples, you put them in the prompt to try to improve your performance. The 3 things I want you to remember: including few shot examples does help. Something is better than nothing in almost all cases. But how you optimize your few shot examples really does matter. Use real annotated examples that you or some other trustworthy authority came up with. I would avoid synthetic ones unless you absolutely have to. Make sure that it's a small, diverse, and representative pool, and be thoughtful about how you order them. Okay, try a couple of different orderings, see if it impacts your performance on a small annotated test set you've put together. Okay, the last thing is, when you're giving exemplars, try to keep your instructions simple and human validated. It's better than not providing any instructions at all. Okay, so we've gone through the first 2. Now let's talk about the third one, which is thought generation. This refers to a range of techniques that prompt the LLM to articulate its reasoning while it's solving the problem. And so that we're clear, thought generation and chain of thought are kind of synonymous terms. At least as far as I'm aware, they're used interchangeably in many instances. And within chain of thought, there is a partitioning of zero-shot chain of thought techniques and few-shot chain of thought techniques. We just went through zero and few-shot techniques outside of chain of thought, so you should know the distinction between those two by now. At its simplest, these zero-shot chain of thought techniques are usually some derivative of appending a thought-inducing phrase to the end of your prompt, something like, let's think step by step. You've probably heard anecdotally that phrases like this help. A lot of the zero-shot, especially the simple zero-shot chain of thought techniques, basically just do this. They ask the language model to think step by step. There's also a few-shot chain of thought techniques where you include exemplars featuring the question and then what a valid reasoning path is. So if you were going to do the step-by-step reasoning to get to the correct answer, you give them some examples of what those steps are. Okay. This chain of thought has been found in several of the studies to significantly enhance your LLM performance, especially when we're talking about mathematics and reasoning tasks, where a lot of what's written on the training sources that these language models pull from give step-by-step reasoning, right? If you were reading a logical treatise on a topic or reading a mathematical proof, they tend to provide things step-by-step. And so appending this string to the end, let's think step-by-step, sort of primes the language model to think in those ways. Okay, so let's take the two, starting with zero shot, and work our way very quickly through some of the techniques. A lot of these are pretty simple, so I'm going to cover them quickly. There's a technique called analogical prompting, where you self-generate relevant examples and exemplars in the context before solving the problem. So this is regular old zero shot. You can see here, you just include the question you want to answer. There's no examples, right? This is distinct from zero shot chain of thought down here, where you just append, think step by step. That's what I mentioned earlier. That's the simplest way to get a zero-shot chain of thought. The authors of the paper where analogical prompting was discussed basically say, instead of putting think step by step, ask an LLM to come up with instructions to recall relevant examples and solve the initial problem. And that when you do this, you insert those relevant examples here, and under solving the initial problem, it will return to you the result. So very simple technique. You're basically just asking it to come up with instructions to choose examples on its own, as opposed to saying think step by step. And they report that this little tweak ends up improving the performance on some tasks. Okay, there's another one called step back prompting. By the way, these zero-shot chain of thought techniques have a lot in common with just general zero-shot techniques. They're always these very simple tweaks that you make to prompts. So what happens here is that the LLM reviews relevant concepts and facts before starting the chain of thought. So if you have chain of thought here as an example, and you have step back prompting here, the distinction is that in the first step, you take an original question, such as what we're showing here, and you ask a relevant background question. In this case, what was the person in question's educational history? This is important if you want to know which school they went to between August of 1954 and November of 1954. So you basically ask the LLM to come up with these step back questions and to generate answers for those step back questions. So you append those basically to the original question and you generate the final answer. Very straightforward. They report that this technique, which is probably reminds you of some of the things we covered in just regular zero shot without chain of thought, they say that this taking a step back and appending the additional relevant information improves performance on reasoning benchmarks. Okay, there's another technique called thread of thought, which segments and analyzes extended context. This is very similar to S2A that we covered in regular zero shot. You have a large passage here, a large input, and what you do is you ask the thread of thought to select the pertinent information from here before generating the final answer down here. Okay, so two-step process, figure out what's relevant, that comes over here, and then come up with a second output that answers the original question using the relevant input. Okay. Tab-CoT helps when you have tasks that require some kind of numerical reasoning or tabular reasoning. So think of the kinds of tasks you do in accounting or finance. Basically, all you do is ask the language model to represent the text as a table. So if this was the original question, you have a first step where you say, hey, take this and try to turn it into a table. In this case, it's a markdown table. You then ask it to answer the original question using the markdown table that it generated. And they report that this ends up actually getting you better performance on tasks, particularly when you use code-tuned large language models. Okay, that covers actually all of the zero-shot techniques. So now we're moving into some of the few-shot chain of thought techniques. So again, remember the distinction between zero and few-shot is what? No examples in zero-shot, some examples in few-shot. I'm similarly going to go through these quickly because I think they're all pretty, they're intuitive to understand. And the most important thing is that you're aware of what these techniques are and can get inspired by some of these as you're solving your own problems. So let's start with active prompting. I actually like this one, although I think that their technique is a little bit of brute force. So what they do is they take n different kind of groupings of examples, okay? And what they do is they pass those groupings over here to ChatGPT, but they pass it to ChatGPT or some other LLM multiple times, let's say 5 times. And each time they pass it, they ask it to answer the question that's embedded within the few shots. Because, right, if these are shots, we have both the question and we have the answer. That's why we're giving them as examples. And what we're trying to figure out is, for which of these questions was ChatGPT the least confident? So meaning it kind of switched up its answer when you asked it multiple times. The idea is that if it changes its answer frequently, here, it's very unconfident. If it gives exactly the same answer 5 out of 5 times that you gave it the question, it gives the same answer, it's very confident. And if it's something in the middle, then, it's somewhat confident. And what they propose that you do is you ask the language model to do this for a set of questions. And then you have the humans annotate the places where there's high disagreement. So over here, you have humans basically annotate more few-shot examples that look like these two to include in the prompt, and less few-shot examples that look like this one, where when you asked it, it consistently got the right answer. It's very intuitive to understand. Like, if you're going to give examples to your language model, what kinds of examples do you want to give it? You want to give it examples that will help it avoid a mistake that it's likely to make. And it's more likely to make a mistake on a place that it's unconfident than it is on a place where it's very confident. So that's the idea. Pretty simple. Ask it multiple times, see what kinds of questions it messes up on, give it more questions like that in the few-shot examples. Okay, ThoT is a zero-shot prompt that generates a chain of thought. Sample shots based on some selection criteria. So here they say if you have a set of candidate questions that you can include as exemplars or the shots in your few shots, well, they suggest that you sort of cluster these, very similar to what you saw in one of the earlier examples in just regular few shot. You give that to an LLM, and then you have the LLM choose basically samples from the clusters. Okay? These end up by getting you a more heterogeneous set of chain of thought samples. You tend to get a better result, is what the authors report. There's a complexity-based selection criteria as well, because taking a step back, these few-shot techniques are all about how you choose the right examples. If you're going to include examples, just like we spoke about before, how do you order them? How do you make sure that they're the most relevant, the highest quality, the most diverse? All the few-shot techniques are trying to solve that problem. Here, what they tell you to do is just ask basically the LLM multiple times, take the majority answer over a set of generated chains. So what I mean by that is you ask it specifically to come up with 3 or 4 or 5 solutions to a problem. And then you come over here at the end and you look at, of those chains that were the most complex, see this one took 6 steps, this one took 5, this one took 4 in the answer, which, you look at for the chains that were the longest, the 3 longest, what was the most popular answer? In this case, it was 200, so they say the answer is 200. So pretty simple. Ask for it to do the reasoning multiple times, get the most popular answer from the longest reasoning chains, and use that one as the answer. It's kind of like a voting technique. Contrastive prompting is another few-shot example where you show the LLM examples of both how as well as how not to do the reasoning. So it's basically akin to inserting negative examples within your few shots. This is helpful only if your language model in some of your testing, there's a corner case that it really tends to fail on. I think surgically inserting examples of the wrong way to think about a problem is helpful there. Otherwise, I don't think that the contrastive is actually that helpful. Memory of thought here refers to a technique where you take a large unlabeled corpora of training exemplars to build few-shot prompts at the test time. And so the way this works is you have your unlabeled data set. This is what you want to, your movie reviews that you want to label. And you have your language model look through this unlabeled data set and generate some chain of thought. So you give it, for example, one of the points, you ask it to generate the step-by-step reasoning it's going to use to solve the problem. Just like we did before in the assessment of confidence, right? They similarly have you do an uncertainty filtering after this step. So if it contradicts itself when you ask it across 4 chains of thought that it generates, if it contradicts itself 3-4 times, then it's probably not very confident. You want to take the ones that, in this case, it was highly confident about, and you want to store those as memories. And then they're arguing that you pull from those memories as a function of the properties of the question at test time. So you're basically dynamically, for each of the questions you want to answer, you're selecting a memory, which is a pre-approved kind of unlabeled data set and chain of thought that accompanies that as an example, as a function of what the question type is. That's the idea of memory of thought. Uncertainty routing is where you generate multiple reasoning paths, and then you assess all of them and aggregate the output. You could do that by choosing the one that does best as a function of some score, or you could do it by averaging the responses or voting. So we've seen versions of that in previous examples. Prompt mining refers to taking a prompt and trying to do an analysis over the specific words used in the prompt to replace those words with ones that are more common in the corpora that are used to train large language models. There's sort of a subtle reason for this. The idea is that if you use language that's more common in the domain that you want to solve the problem in, the language model should be able to pull from a larger set of relevant examples from its pre-training data. And so basically prompt mining refers to techniques where you come and you try to find individual words inside of your prompts, and you figure out how you can replace those words and what the impact of those replacements will do to the performance of the model. I think prompt mining is a bit of overkill unless you're, you really want to get into prompt engineering as a business. Okay, the last of these that we're going to cover is a general purpose few-shot chain of thought technique called auto-directed chain of thought. And what you do here is you come up with a definition for some concept that you're interested in. In this case, it's entrapment. And then what you do is you have an algorithm look through for each question and answer pair within a pre-labeled set of examples that you could put in as shots within your few-shot prompt. You ask the language model to do labeling of the questions in those pairs as entrapment or not. And so you see you have the entrapment definition here. So in this case, you're asking it to label as entrapment or not. If the model does it correctly, then you ask it to generate the reason that it came up with the answer here. If it does it incorrectly, then you ask it, you tell it that it was wrong and to explain why it was wrong. Okay, you store the question, the answer, as well as the reason R here within a tuple. So instead of having a set of examples that you could pull from now with questions and answers, you have questions, answers, and the reasons that the language model got it right or got it wrong. And then what you're supposed to do is insert the questions and the answers within your prompt. That's what they're showing here on the right-hand side. And note for the ones where it got it wrong, what the reasoning was. And this is supposed to help your language model avoid making reasoning mistakes that you observed in your annotated training examples. Okay, I know that one was a lot. I promise the rest of them are shorter than this. If you've made it through this point in the lecture, it's downhill from here. 3 things I want you to remember about thought generation or chain of thought. The first is that you should use chain of thought for, let's call them conventionally harder problems, things that require mathematical reasoning, logic, things that don't just ask for the final answer, but require some step-by-step reasoning, and therefore asking the language model to think step-by-step will help. Okay, you should use chain of thought, or when you're using chain of thought, you should use shots. In fact, just in general, when you're doing prompting, you should use shots or examples to improve your performance. The last thing is, it's really important to validate and adapt. Test multiple strategies, stick with what works best for your task. Okay, so we've made it through the first 3 of these. Let's move on now to ensembling. This is at its simplest, a set of techniques where you prompt multiple agents and then you aggregate the results. I'm going to cover a few of these, not all of them, because some of them are redundant. As you probably noticed, even as we covered the last section, some of these are redundant with things we've already covered. And to spare you from having to see the same idea re-represented, I'll try to cover the ones here that are a little more novel compared to what we've already touched on. So this is called demonstration ensembling. Just as a reminder, you can see the paper here if you're interested in learning more about this in all of its grueling detail. The technique is pretty simple. You create multiple few-shot prompts, and then you aggregate over their outputs for a final response. So as opposed to sort of the standard way where you create a prompt, and then you have a question here, which you feed to an LLM, you have multiple smaller prompts with less examples, and then you aggregate over those to get a probability of the answer. Okay, very straightforward. There's another technique in ensembling called max mutual information, where you basically come up with a large set of prompts, and then you choose among the prompt templates the one that maximizes the mutual information between input and model output, If you don't know what mutual information is, please feel free to Google it. It's an information theoretic measure between two signals, or in this case, text. Okay, the key thing I want you to remember here is that if you have higher mutual information between the input and the model output, it tends to improve the task accuracy. That's what they identified. So if you have a set of templates and you have some annotated data, you might want to look for the ones where, as you put in your input, you tend to have a high mutual information between the input text in your template plus the question you're answering and whatever the model outputs. That's the indicator that you have a good prompt. Okay, this third idea, mixture of reasoning experts, is actually so straightforward. You basically take a set of language models. We're going to be doing this in the homework actually, but not really with voting. And each of them has a different specialty. They've either been fine-tuned to accomplish a task, or their prompts are slightly differently. Prompts are written slightly differently. And you ask each of them to answer a question, and then you basically have a paradigm to count up the votes and synthesize those to get a better answer. What they found is that routing these queries to specialized experts can improve task accuracy over a single expert. So meaning, if as a function of what the task is here, you weight sort of which of these experts has a more valid opinion, including even just selecting one, like we'll be doing in our homework assignment, you tend to get a better performance than if you have all of them. Okay, self-consistency. This is very related actually to one of the concepts we covered earlier. You prompt the LLM multiple times, use a majority vote over the responses. Nothing kind of new here. It's just another idea that, another instantiation of this idea within the ensembling community. There's also universal self-consistency. This is very similar to self-consistency, where you ask multiple times and see if it contradicts itself to get a measure of confidence on the response. But here you allow the LLM to determine who wins the vote instead of counting up the answers. So when would you use this versus self-consistency? It's helpful when the same answer may be output differently by different prompts. So for example, in self-consistency, if we were asking for the answer to a math question or a true-false question, there's only true or false as responses. If we were asking for a qualitative description of a movie review and we didn't say it was either positive or negative, but it could put it in any kind of words that it wanted, it might be useful to take the set of responses when we prompted it 10 times, provide those to an LLM as a final step, and ask it what was the majority answer so that it accounts for the different ways that all 10 of those responses might have looked. Okay. Pretty straightforward. Ensembling is basically, again, you prompt multiple agents, you aggregate the results. 3 things to remember. When you're using ensembles, if you're going to use ensembles, start with self-consistency. Obviously, if you're going to be using a consistency measure in your prompts or across your prompts, you want to make sure that the temperature of your LLM is not 0. And you want to sample your chain of thoughts multiple times. And then let the majority vote dictate what you move forward with. Okay, specialize when your questions vary. So I would build small Moore style ensembles with some mixture of reasoning experts with different prompts per reasoning type. Pick the best answer with the highest agreement or learned selector. This is going to improve your cross accuracy, your cross-task accuracy over any single expert that you choose. And finally, if you're computes type, I would just choose one strong template via max mutual information exemplars. That is to say, you may not want to run your prompt 10 times to get a measure of which response was most popular as a way to get the best answer. You may want to just have one prompt, in which case you can use the max mutual information technique to try to figure out what that best prompt might be. Okay, we've made it through ensembling. 2 left to go. Let's go to self-criticism. First of these, chain of verification. Here you generate an answer, generate related questions, and then verify that those are correct and have the LLM reason over the whole set. Example that's shown here is you want to name some politicians born in New York. You use that to get some responses. You then, for each of the components in this response, you can see Hillary Clinton, Donald Trump, Michael Bloomberg, you ask the LLM to go off and do a separate verification step. Okay, so you ask it, hey, where were these people born? Okay, it comes back, it gives a response. You can see in this case, Bloomberg was born in Boston. He was not born in New York. Hillary Clinton was born in Chicago, not New York. So you take this set of verifications along with the original baseline response, you include those together and generate a final one. So what you're doing here is very similar to ensembling, by the way. You're trading accuracy for compute. Ask more questions, add more steps to the prompting process so that you get a higher quality output. Self-refine is similar philosophically. What you do is you ask an LLM a question. Got one here, for example, I'm interested in playing table tennis. You get a response. You then have an LLM issue some feedback on this response. In this case, it's, hey, this is engaging, but provides no understanding about table tennis or how to play it. So it's trying to pretend that it's a critic. It's you, right? It's like it's simulating what a critic would say to this response. It then, using that information, asks for a verification of this and regenerates the response, trying to do it better this time, okay? So you can see it went from, it's a great way to socialize and stay active, to, it's a fun sport requiring quick reflexes and good hand-eye coordination, okay? Another example of this is shown here with code optimization, where it's criticized for using a slow brute force approach, and it refines it. Very simple idea, right? You take the output, you ask the LLM to criticize the output and regenerate, and you keep doing this until you hit some criteria to stop. The last of these techniques that we're going to be covering under self-criticism is to create sort of three distinct LLM roles or personas that do three different tasks. One proposes steps to solve a problem, starting from a set of, let's say, three presuppositions here. The second one verifies that the proposal is okay. And the third one decides when you've solved the problem. So when do you stop proposing new steps? So those are so three kind of distinct LLM roles. The example they're showing here is that maybe given these two presuppositions, 1 and 2, it implies that the next step is A. Okay, there's a separate language model that, very similar to the example back here where you had the feedback, comes in, does a check and says, okay, this step's all right, move forward. And you keep doing this over and over until you have the reporter who decides, hey, we've solved the problem, we've got enough, let's stop. Okay, and that gives you a stopping criterion. The authors reported that this cumulative reasoning task significantly improves your performance when you're talking about challenging tasks, such as breaking down three LLM, let's call them roles or personas, and having them in sequence interact with each other's outputs boosts your performance. Simple idea, but pretty powerful. What I suggest you do with self-criticism is you start cheap, expand only if you're uncertain. Okay, so maybe you sample 3 chain of thought runs, you use majority vote, you add a self-criticism pass only if you're having a problem with consistency across your 3 votes. Because if you're asking an LLM to solve a problem 3 different ways or 3 times, it's giving you exactly the same answer each and every time, you probably don't need to add these fancier prompt security techniques to improve your performance. Okay, so we only have one left, it's decomposition. And this is about breaking the prompt into its subprompts. So let's start with the first of these that I think is worthy of us reviewing so that we don't have redundancy. It's the least to most strategy. So the LLM formally generates subproblems and then sequentially solves the subproblems appending to the prompt. So stage 1, you decompose a question into sub-questions. Here you can see the decomposition into sub-questions, the green as well as the orange. You take the green question, how long does a trip take? You have a language model solve this question. You take the answer, you append that answer back into the question along with the next question in the sequence, and you move forward. So what the language model is doing here is it's sequencing the questions. Hey, which of these do I need to solve first? And then how do I do the appending in sequence so that I get a better response? Program of thought is the second example that we're going to cover from this set, which basically so simple. You just ask a large language model to represent the question and the reasoning steps as code. It's really good if you have things that require mathematical or symbolic reasoning, representing the problem as code, and being able to check if the code compiles or executes can improve the performance on tasks pretty effectively. Tree of thought is another one that we're going to cover or go through, which is where you explore problems as a tree of possible reasoning steps. You keep and expand the best paths. So what you do is you propose, for example, a series of steps using chain of thought to solve a problem. You only go, or you ask for it to propose 4 different chains of thought to solve a problem, 4 approaches. And you go and you look at each of those. And from each of those first steps in the chains of thought, you compare across them to see which does the best. Let's say this one does the best. So you might ignore, for example, the one that does the worst and let the one that does second best run in parallel. You then go and you ask this one to continue to its next reasoning step. If it did the best, maybe you ask it to branch into additional reasoning steps, additional steps from there. And you repeat this process until you get to an output. At each of these steps, of course, you are asking an LLM to come up with what the next step is in the sequence to solve. And you're then having an LLM solve each of the sub steps that follow after that. So this one can be very computationally expensive. You have to make a lot of calls to a language model. It has been found to be very effective for tasks that require search or planning, but of course it comes, like a lot of these techniques, at cost. Okay. So my suggestion here is that if you're going to do decomposition, you make sure that you keep the steps short and very atomic. There's no point decomposing the steps in a reasoning or a task if those individual steps contain multiple components. So if you're going to decompose to the shortest, most atomistic components of the tasks that you can accomplish. So with that, congratulations, we've made it to the end of the steps. We've covered all 6 of these. You basically at this point know all of the techniques that are used in prompt engineering as of 2025, and contexts in which they've worked, as well as contexts in which they've not worked. That's it for today's video. I'll see you in the next one.